doing acoustic metrics for a decade, not the 2 decades that Tony expected, but for about a decade and a half or 2 decades before that, I was involved with Navy acoustics and detection of different kinds of signals. So the acoustic metrics and indicator stuff is actually a pretty natural follow-on to that kind of detection work. So what I want to talk, right place. All right, so what I want to talk to you about today is soundscapes, and it will primarily be the marine soundscapes over here on the right. But I think we have to pay attention to sort of the other 2 significant groups of types of soundscapes you will see in the literature, which are human and terrestrial. When you see people talking about the human soundscapes, they're really talking about trying to make an environment appropriate for a human use. So if it's a park, they want it to be quiet. If it's a library, again, quiet. If it's an urban street, then you're expecting there to be more noise, but maybe you're trying to get noise to be quiet in the evening or nighttime when people are sleeping. So it's all about perception. It's all about what is a space going to be used for. There are standards for how they do the metrics and how they collect data on human perception of the space and what it's supposed to be used for. And that's all standardized in ISO standards, and it's a very advanced field. The terrestrial soundscape, probably need to mute out there. The terrestrial soundscape world, a lot of the work that I've seen in the literature on that has been focused on trying to understand biodiversity. So it's really about how many different species are there, trying to get surrogate metrics from sound that let you know that kind of information. There's also definitely some work on the effects of human noise or the presence of human noise and environmental noise, but it's really been focused on trying to understand biodiversity and spatial diversity in soundscapes. And then we have the marine space, which is where a lot of us primarily work. And in that space, it's almost a blend of the 2, because we want to know about biodiversity, but there's a growing need to understand the effects of the human sound sources on the biologic receptors, what kind of sounds they're making, but also how they perceive the sounds from other biologic sources and from people so that we know how they're going to react. So in the human context, I really like using this particular figure for all of them, but it comes from the human context from Jennings and Kane. And they broke sound into the sound, which is the engineering metrics. It's measuring things. And you'll see there's values there like the dBA weighted or the LAQ, so the weighted level is weighted equivalently, and things like loudness and roughness and intelligibility. And then the combination of sources and their level of expectation and whether they're in the foreground or the background and whether they're expected and whether a receptor has encountered this particular sound source before, that becomes part of what they broke into scape. And so it's this combination of engineering measurement plus perception that makes the complete soundscape. So there's clearly an evolution of over time that's built into this, and it's a sum of sources, and it's all about context. When we look at large environmental data sets, we'll often have 7 to 20 different recorders that are out for anywhere from a month to a couple of years or 3 years, and we have this large pile of data. And the objective of the soundscape analysis is to turn that into a series of metrics that mean something. We get some information, and as we get more information from either dedicated experiments or from these large data collection projects, we learn to evolve the metrics and get more information that means more to the receptors. So obviously what you're going to measure is going to change with each application, and there's going to be a feedback loop as we learn more and more in each application. The applications of acoustics for environmental observation can really span a whole diverse range, and I think there's people in this seminar series that cover most of these. We could be looking at presence of vocalizing life for density estimates, for spatial distributions or habitat usage or partitioning, the presence of human sound sources and trying to measure their effects, temporal cadences of different kinds of sources. We could be looking at baseline measurements and changes over time and space due to human activity or climate change. We could be trying to take things to a different level and measure the temperature profile or density profiles of the environment, which at least in the marine case is being used to measure climate change and heat storage in the oceans. Or we could be probing sediment properties. That occurs both on land and at sea to try and understand what either the surface layers are or going far down into the subsurface to look for oil and gas. zooming in a little bit on the effects of human sound. I think most folks in this seminar will be familiar with this zone view of the effects of human sound, where you have a zone quite close to the source that's loud enough to cause physical injury, death, or permanent threshold shift. Then we move out a little bit, and there's a zone where temporary threshold shift can occur. Then we have a zone where masking can occur so that the animals cannot hear the sounds of interest, be it from themselves, from conspecifics, or from the environment. Then there's areas where there's potential behavioral disturbance and or physiological responses like a stress response. Most folks now will say that this particular view is overly simplistic and not perhaps the best way to describe the effects of sound, but I think it's a good starting point. Some of the kinds of things that you could encounter would be, say, an animal having a behavioral reaction that leads to an adverse effect, like, say, stranding in a marine mammal, or running into a highway for an animal. So they responded and they wound up being killed, which would be a zone 1 response due to a zone 4 type activity. So to give a practical example of some measurements that we've made here at JASCO, and how soundscape analysis has been applied, and then how we would want to understand this data better if we can do a better job of soundscape analysis. I'm showing here data of 4 different species. So you can see the species names in the top right-hand corners of each plot. And for each one, there's a measurement 2 kilometers and 20 kilometers. And this is from a drilling activity off of the Nova Scotia performed by BP in 2,300 meters of water. And so for each one of the plots, you can see time across the x-axis in days, but it's also on the y-axis as time of day. And so what we're plotting here in gray are automated detections of the animals, and in black are places where we went in and our manual validation said, yes, there are in fact animals there. And what we're seeing in this data set is a huge difference in presence, 2 kilometers versus 20 kilometers away. So to get here, we had to use very specialized detectors and then dedicated manual analysis. And one of the things that we'd like to get to from some kind of soundscape analysis and metrics would be simpler ways of getting the same information. And then can we use the soundscape information to predict and understand this kind of effect? We're also going to have to probe deeper and say, okay, well, is this a real effect, or are there alternate explanations? Could this just have been masking so we could detect them at 2 kilometers? Were they not vocalizing but present? Would they have been at the 2 kilometer site in the first place? These are the kind of questions that have to be investigated in order to really understand if this is an interesting effect or not. And finally, once we know if there is an effect, then we have to ask the question, well, what's different at the 2 locations? Is it just the sound energy, or are there other qualities of the sound that the animals are reacting to and standing off from the drill platform? I put at the bottom here where this report can be found. It's on BP's public website. So this recordings to information is also, to a certain extent, a physics to biology type process. And as we get more information that we can rely on, then we can build environmental protection regulations. So an example, again, from the marine world, in 2007, Southall et al. Put out a paper that came up with an initial set of weighting functions that were an initial estimate of how different kinds of marine mammals hear, and then they had thresholds for how much sound exposure the animals could be exposed to before either temporary or permanent threshold shift was believed to have occurred. So from that baseline, the federal regulator, the NMFS, looked at that. They commissioned more studies, and in 2016, almost a decade later, they finally put out their first set of regulations based on the basic concept that was in Southall. They changed the weighting functions, they changed the thresholds dramatically, but the basic concepts were there. And it took another 3 years from the initial publication to get to a scientific peer-reviewed publication, which is Southall et al. 2019, that has the same information in it and has been peer-reviewed. In the fish and invertebrate world, where there is something like 35 times more species than there is for marine mammals, Popper et al. 2014 has come out with an initial set of recommendations, but there's an enormous amount of work required before we can get anywhere near a set of regulations that would be appropriate for fish and invertebrates. So the process of going from recordings to information, physics to biology, and looping back and finding these metrics is a long process that will eventually lead to regulations if it's done right. So in today's talk, I want to go through and provide you guys with a understanding of some of the popular soundscape metrics that have come out primarily from the terrestrial literature, which are the ones I'll focus on are entropy and the acoustic complexity index. And then I want to look at sound exposure level as a soundscape metric, which is some recent work I've been doing, and then put out some challenges on what soundscape qualities will we want to quantify moving forward. So, investigating the performance of soundscape metrics using known data sources and numerical simulations. And this is extracted from a presentation I did with Dave Barclay at the ASA meeting in New Orleans in November 2017. So pretty much what I've mentioned already. The motivation for this work was to follow on from the terrestrial world and their work and try to use acoustic metrics to identify biologic diversity and the effects of human activity in large passive monitoring, acoustic monitoring data sets. The need here is for effective metrics or indices in order to decrease the analysis effort and improve interpretation of the data sets we've collected. The particular thing I was doing with this analysis was understanding the information provided by the entropy and soundscape ACI metrics. So for this particular analysis, I was doing two things. One, using simulated data, but also going back and looking at unknown data set. In this case, the data was collected off of Newfoundland at the edge of the Grand Banks, looking out into a canyon. It was from sort of 1st of September to mid-October. And there are sort of 4 sources that we knew were in this data set. Down here in the sort of 20 hertz range, you see the building of a fin whale chorus. Up in the 60 to 100 hertz range, we have humpback whoops, which they do in this area in the fall. Just long series of very low frequency grunts. And then there's lots of sharp red vertical lines here, which are the ships, and the coming and going of different weather patterns. And I think there was a tropical storm that went through over here in early October. So examples from terrestrial core release soundscape analysis has shown great promise for use of metrics, especially if you have things like what we show here, which are sort of choruses from the fin whales and the humpbacks. So we want to see if we can detect those. One of the metrics that's reported fairly often is the acoustic entropy index, which is the Shannon entropy, and it's the sort of numbers of bits of information times a logarithm, the natural logarithm of that number of bits of information. And there's a lot more information on entropy and marine mammal research in John Buck's presentation from this time in 2017, which are available online through the Environmental Acoustics page. What this metric says is if you can come up with a metric that represents bits of information, the way the sequential bits of information add to that total information is not the square of the bits, but the number of bits times the logarithm of the number of bits. So folks have tried to apply this to acoustic analysis. And one of the more successful applications by Villanova, they took OI as the occupancy in each frequency band I that exceeds a detector threshold over a 5-minute integration time. So that really is an energy indication, but by using the 5-minute windows and frequency bands, they kind of make it into bits of information instead of just energy. And it showed to be quite useful if you're trying to get at an acoustic niche type analysis. So if you have an environment where there's one animal at, say, 1 kilohertz, another 2 kilohertz, another 4 kilohertz, and one uses dawn, and one uses dusk, and one uses mid-afternoon, like a cicada, say, then this kind of energy analysis or entropy analysis is pretty effective at pulling out those courses and giving an idea of biodiversity. There are variations on that of the temporal entropy or the frequency entropy. In both cases, you're defining some kind of a frequency band and a time analysis and applying your analysis to those bands. There's another one that's gaining in the number of times you're going to see in the literature. That's kurtosis beta, which is defined as the 4th moment of a time series divided by the square of the 2nd moment. And this is really good at detecting peakedness or impulsiveness. We'll come back, I don't analyze that in this section, but I do come back to introducing it later on. And then there's the acoustic complexity index, which has gained a lot of traction, and you see quite a bit of papers on it. That definition I show here is the initial definition from Farina. I think it was in 2009 or 2008. And it's the difference in the spectral amplitude between 2 time bins at some frequency divided by the amplitude in one of the time bins. He subsequently came up with a second definition in 2016 that acknowledged the fact that uneven use of the energy in the denominator led to some pretty wacky levels, which we'll see in some of the examples. And so there's this ACI FT2, where you're normalizing by both of the energies that you're subtracting on top. So in order to understand the properties of the ACI, I'm going to go through a bunch of examples, and I think you'll see then how the choices that are made in defining the metrics have a dramatic effect on what the ACI outputs. So for these examples, I'm going to use either Gaussian or pink noise as the base data, a minute long, and then add different kinds of 1 second signals. There will be either 110 or 60 copies of those signals, and I'm going to apply them to different bandwidths. The types of signals are going to be a frequency upsweep, band limited depending on the band we're adding to, or a downsweep, or a continuous wave, just a tone, or a series of impulses, some number of impulses, where the impulses are running from 100 to 5,000 hertz, essentially as a 0.01 second upsweep is how they were implemented. The analysis band is considered to look at the fact that the ACI has an explicit definition of frequency band in it. So I'm going to take bands of either 10 to 40 hertz, 40 to 200 hertz, or 200 to 2000 hertz, and then add different bandwidth signals into it. So pretty ugly figures here that I'm going to walk you through, but just to orient you what these are showing, we have the three bands, 10 to 40, 40 to 200, and 200 to 2000. Then the color indicates the kind of signal that was added, either the CW, the FM downsweep, FM upsweeps in green, and the impulses in blue. And then there's a bunch of detail in here, which is relatively insignificant for now. And when it becomes important, I'll zoom in so you can see it. So first here, the Gaussian noise, we're seeing levels that in a case over here with one of the FM upsweeps are reaching up to 3,000. So that's a dramatically large number. It's very hard for an index to make sense of that when you have a whole bunch of other numbers down here, which are in the 1s, 2s, and 10s. So scaling and trying to determine what to do with the baseline ACI FT is difficult. If we put pink noise, we get significantly different responses, which is not highly desirable when you're coming up with an index, and it's important to be aware of that. Okay, so if we then move to this normalized, the divided difference formulation, things get a lot more predictable and balanced. You'll now see that the average value becomes 1, which is really nice, and you get deflections up and down. There are definitely differences in the amplitude still with the Gaussian or the pink noise. For instance, if we look at this CW case over here, you're getting to about 0.4 and 1 in the Gaussian case, but only maybe 0.7 in the pink noise case. The first thing we see is that there's definitely a difference in sign between the CW and the impulses or the FM sweeps, where the CW is decreasing the ACI and the impulsive signals are increasing the ACI. If we have the same bandwidth, but mixed in signal mixed into a different bandwidth of noise, we get a different ACI. So the arrows here are pointing to an FM upsweep that is 30 hertz wide. In one case mixed in with a 30 hertz wide signal, that's the 10 to 40 hertz band. And the other case mixed into a signal or a bandwidth that's only 40 to 200. So it's only a fifth of the total space. So we see a dramatic difference in what the ACI is producing. Okay, hold on. Yeah, okay. So now to zoom in on that a little bit, I've switched the orientation of the figures here so you can start reading some of the text. Again, it's a lot of information, but essentially it's a type, it's the band, the number, then the type of noise, and the SNR. And then the 10 to 40 hertz, and then the 4200 and the 200 2000 are now oriented vertically. So if we look at the CW case, now this is either 1, 4, or 10 CW tones mixed into the 40 to 200 hertz band. And we went with an SNR of 10, 3, and 0. So what we're looking at is the same SEL, but with different amounts of signal mixed in. And we see that the ACI decreases pretty dramatically as you add more and more signal, even though the total sound exposure hasn't changed. Looking at it a bit differently, now we've fixed the number of tones, but changed the signal-noise ratio. We don't see nearly the same kind of changes. So again, the SEL is a second-order effect. comparing again for some FM sweeps. So here we have either 1, 10, or 60 sweeps mixed in at either an SNR of 17, 7, or 0. So again, we have constant SEL. We see that it's the number of tones, or number of FM sweeps, that's increasing the ACI. If we look at bandwidth and signal type, so here we're just looking at the FM1, but you see that as the FM down sweeps, as the bandwidth of them increases, the ACI increases. What if we flip the order of the operation here? What's going to happen? So now instead of doing time first and frequency second, we do frequency first and time second. What happens is that the magnitude of the effect changes and the sign of the effect changes. So now CWs are causing an increase in the ACI, and tones or sweeps are causing a decrease in the ACI. Fairly intuitive if you look at the frequency time combination of how it's going on. We also see there's a pretty dramatic change in the scale of the effect. We're getting a lot more with the ACI FT2 than we are with the TF2. But that really has to do with how the FFTs and the time durations are matched. And you can kind of see that if we now change the FFT size. So most of the stuff I've been showing you has been using a 2-second FFT or a half-second FFT. If we go to a quarter-second FFT, the amplitudes change. In the CW case, we're getting more. In the FM case, we're getting less amplitude in the ACI. And it has to do with how well matched the FFT bins are to the total bandwidth and to the rate of change of the signals. The other thing that's kind of interesting you can see is that in this area here, all the signal was supposed to be in this second band of 40 to 200 hertz, but we're winding up getting a bunch of leakage, spectral leakage now with bigger FFTs down into the 10 to 40 hertz range. So what have we learned on the ACI? We need to express it as a divided difference to stabilize its values. That what it's really doing is detecting the percentage of signal per unit time. That continuous signals will decrease the ACI below 1 and impulsive will increase them above 1. That SNR and SEL is a second order effect. That response is going to depend on background noise as well as the signal. And then it really depends on matching the underlying FFTs to the kind of signals that you're trying to look at in the first place. The noise one here is actually pretty important. If you happen to have data where your environmental noise and your system noise are approaching the same amplitude, the ACI will explode on you. You'll get all kinds of crazy values out of it. And that did come out as a admitted effect in Farina's 2016 paper, to the point where they won't even analyze anything that's not 30 dBs above their system noise, because the values are not dependable enough. Okay, so if we come back to that humpback and fin whale and vessel data set, using the same bands, the 10 to 40, 40 to 200, 200 to 2000, and then I threw a top band of 2000 to 8000 since we have 16 kilohertz data. You're seeing the most signal. So what I've done here is computed the 1 minute ACIs and then plotted the box plots for across the day through this deployment. We're seeing the most interesting effects on some of the days when there's vessels present in the 40 to 200 hertz range. And we see a little bit of positive effect from the whales as they go by later in the deployment. Same thing down here, the 10 to 200, or sorry, the 10 to 40. It's the fin whales coming and going, which seems to be causing some variation in the total signal level. So the ACI is able to tell us a little bit here, but especially once we get into any higher bandwidth stuff, we're really not seeing much in these top two. So what we've got is that the ACI at least, and really I think you can extend this and say the same thing about the entropy, is that they're detectors in disguise. And the parameters you choose have to match the signals you're looking to get. So you're not going to be able to find a set of values for these ACI or entry indicators that are just going to find everything for you. That isn't possible. It's also important to know that they are relative indicators because they respond to different kind of noise profiles differently, or if you've got two competing kinds of noise, you are not going to be getting any absolute values that are meaningful. They're just a relative indicator. They do appear to have a good use if you know what you're looking for and you're looking into acoustic niches. That's probably going to work. And especially at lower frequencies, you can probably use them for some kind of a soundscape character indication, with that negative for continuous sound and positive for sweeps and impulsive type signals. So again, it's not a huge surprise that this has worked well for terrestrial biodiversity where we have a lot of coursing, but it hasn't worked fantastic for many marine applications, except perhaps for coral reefs, which again have a coursing kind of behavior associated with them. So the entropy is kind of like an energy indicator, since it has two factors that are multiplied together. And the only indicators that we have, the only metrics we have that are accepted and used for regulations right now in the marine world are to do with energy. So what I want to look at now is whether the sound exposure level, which is the energy, can also be used as a metric for looking at soundscapes. The fact that it's being used for auditory injury is because sound exposure level has been shown, especially in chinchillas and in humans, to be linked to hearing injury, both permanent and temporary threshold shifts. And it's based on this thing called the equal energy hypothesis, which states that the amplitude and the duration will lead to hearing injury if it's above a certain threshold. So if there's equal energy, you get equal hearing damage, whether it's long and low level or if it's high and short. There are lots of violations of this that have been found. So things that are very low and very long, or very short and loud, can both have more effects than the things that really follow the equal energy hypothesis and sort of in the middle. There's also been quite a bit of research that's found that impulsive signals have more effect than non-impulsive. Again, both in humans and in chinchillas, as well as in dolphins and porpoise. There's also been a lot of work showing how different kinds of animals can protect themselves from impulsive signals if they can predict them. In the case of bats and dolphins, they're going to use neural attenuation as a primary defense mechanism, so they basically can predict when the sound's coming in and then reduce their neural response. Many mammals also have the ability to lock down their stapes, lock down their stapes so that they don't transduce sound from the outer ear to the middle ear to the inner ear, and so by that way they reduce their sensitivity as well. Just make sure we're all on the same page. Sound exposure level is 10 log 10 of the integral of the power over time, which is pressure squared divided by some reference time and reference pressure. In the case of underwater acoustics, we're using T naught as 1 second and P naught as 1 micropascal. So you have dB 1 micropascal squared seconds. But of course, in the in-air world, in the human world, it's typically 20 micropascals. That's the reference. Again, using the human world as a reference, most of us probably have heard the term dB A-weighted, and A-weighting being a reflection of how humans hear, roughly with a bandpass of 300 to 3,000 hertz. There's been an awful lot of work go into marine mammals, and for marine mammals, we now have a set of auditory frequency response curves for them as well, divided into 6 groups, of which normally analysis is only applied to 5. They're shown here, which is the low frequency cetaceans, that's your big baleen whales. Then you have 2 groups of pinnipeds, or seals, the otarids and the phocids. And then you have the 2 groups of donocetes, the mid-frequency and the high frequency, where the mid-frequency is your delphinids and your high frequency is your porpoise. So if you look at these hearing response functions, you'll see that each one of them is 1 to 2 decades wide, so 1 or 2 multiples of 10, because this is a log frequency plot. The low frequency cetaceans are essentially a bandpass filter from, let's say, 150 to 15,000 hertz, if we use minus 10 dB as the bandpass. The seals in red and green, they're more like a kilohertz to, say, 30 kilohertz. And then the adonocetes are either 8 or 15 kilohertz up to maybe 100 to 200 kilohertz. So I think a really important thing to look at here and realize is that sort of a quarter of the active space where sound is propagating, in the ocean at least, from 10 to 100 hertz isn't used primarily by any of these species. But it is where a lot of human sound is. So that is probably going to have a pretty important effect when we look at the effects of human sound on different animal groups. It also leads to the expression of poor fish and crabs and invertebrates, because they do hear down there. But they have a completely different hearing mechanism that's based on particle acceleration for the most part, which we very poorly understand. So for those who haven't seen them, the NMFS 2018 and SOUTHL 2019 have essentially this table in it, which divides the possible effects of human sounds into impulsive and non-impulsive, and into temporary threshold shift and permanent threshold shift, and then by group. And then there is the SEL for both impulsive and non-impulsive, but for impulsive sounds, there's also a peak SPL threshold. And that is a recognition that sometimes sounds are just so loud, there's an immediate effect. And so if the peak SPL violates or exceeds these numbers, then it's believed that an immediate permanent threshold shift can occur. Otherwise, you need to integrate sound over 24 hours and see if you get to these sound exposure levels. I've used the same color coding as I used in the previous figure to go by group, because you have to, for the SEL, you have to weight the sound by those auditory frequency functions. So in the figures that follow, you're going to see these 5 colors plus sort of an orange color, and that orange color is 410 hertz and above unweighted sound exposure level. So in order to look at the ambient environment, or sort of what happens in the natural regular world right now, I compared sound exposure levels, daily sound exposure levels, for anywhere from 20 to 90 days at these 12 sites. And so we have right here, there's Resolute Bay, which is a sheltered Arctic location. We get 2 sites in the Chukchi Sea, which are right beside each other in different years. We got Baffin Bay, where there's a seismic survey. D&E here off Newfoundland and Labrador are exposed to the open ocean, but also had some seismic surveys and fishing activity in the area. Over here on the west coast, this is in the Vancouver-Fraser Port Authority, so it's right under a couple of shipping lines or lanes in Vancouver. We've got Block Island, 2 sites that were close to some pile driving, and looking at the difference with rain from pile driving. We have Blake Escarpment off of sort of the Georgia-Florida state line. That location is at 800 meters of water and has some local shipping, but mostly distant shipping. And then I've got 2 sites from coral reefs. One of them from 500 meters away from the dive pier and shipping pier, or the pleasure cruise pier in Cozumel, Mexico, and one in a pretty isolated spot in the Great Barrier Reef off Australia. So what I'm going to show you now are a bunch of different plots of the daily sound exposure level weighted, again with those colors and the legends over here on the left, and across time, and again anywhere from 20 to 60 or 90 days. So I'm going to start with the Chukchi Sea in 2014, where there was only 2 ships that went past, and they were distant. So this is pretty much a pristine environment with no human activity. And the variations you see up and down are related to essentially wind and wave activity. So we have some periods where the wind just stopped, and we have levels reaching down to 140 dB per 1 micropascal squared, which is equivalent to about a 90 dB SPL over the day. Very, very quiet. And the levels can get up to about 160, which is a 110 dB SPL. And that's a pretty typical range you could get. Also, you'll notice if you look in here that the black, which is the low frequency weighted, is generally very close to the orange, which is the unweighted. So a lot of the energy is above that 150 hertz. This one next to it is a kilometer away from the previous site a year later. And in that year, Shell was doing a drilling activity looking for oil and gas. And so we were 1 kilometer away from all the dynamic positioning and supply ships and the activity that were going on. And you can see there's a 20 to 40 dB increase in this total daily sound exposure levels for the lower frequency signals. So that platform is making a lot of low frequency energy, and judging by the fact that the low frequency and the unweighted are still pretty close together, a lot of it's above 100 hertz. Another interesting effect you'll see here is the absolute lowest level that we're getting in the Dalhousie weightings are below what we had in 2014. The reason for that is sampling rate. 2014, we were sampling at 250 kilohertz, and in 2015, we're sampling at 64. So there's an enormous amount of bandwidth over here that, if there's no environmental signal, is just adding system noise, which sort of leads back to, you got to be careful how much bandwidth you want to record if you want to really get just ambient levels. And when you apply weightings, you're applying weighting to the recordings you made. So if you didn't record above 30 kilohertz in this case, that's all that's being added in. So now your weighted SELs, you have to take them with a grain of salt. Moving to the left, this is Resolute Bay, which is again 40 or 50 meters deep. It's again ice covered in the winter, but oil and gas activity in this case, but a lot of local human activity of fishermen and hunters zipping around and zodiacs. And so all these spikes you see, low frequencies especially, that's all from local boat traffic zipping around as the fishing and hunting occurs. Then in late October, or late September, early October, the ice just came in, boom, and all that activity is gone. They just left the water, and we have a totally different soundscape as viewed from this SEL. You get dramatically lower levels. You get a few days when the ice opens up and you get higher sound levels, but for the most part, it's quite low, especially for the higher frequencies, because the high frequencies really do not travel well under ice. Looking at the two stations off of Newfoundland, the first one, Orphan Basin, there in the bottom left. So that was a fairly pristine environment up until the beginning of June, when a seismic survey started. And as the seismic survey gets closer, you see the daily SELs go up. And now you see a pretty dramatic difference between the unweighted and the low frequency weighted sound exposures, because there is so much energy from seismic in the low frequencies. You don't see the seal weighted levels start to climb until later in the survey, as the survey gets closer and more high frequency energy from the surveys reaching that site. Carson Canyon, that was part of a seismic exposure study for crab to seismic surveys. And the general environment is very similar to Orphan Basin, where there's a lot of distant seismic surveys going on. So you do see this big gap between the orange and black. But then you see two big spikes, one when the seismic survey overpassed about 2 kilometers away, and one when a fishing vessel went directly overhead, creating, again, a big gap for both of these cases between the low frequency weighted and the unweighted. And sticking with the shipping, what really stands out here in the Vancouver-Fraser case is that you don't see the dramatic variations day over day from the environmental noise. It's all dominated by the shipping, and you get a very flat sound exposure level from day to day. Going to Blake Escarpment, here there is definitely a pretty significant contribution from distant shipping, separating the black and the orange again, but you see significant variation from the environment as well, bouncing up and down. Now here's the two cases from pile driving. This is a much shorter data set, so the stairs are quite a bit wider. The first one, you had pile driving 850 meters away, and when the pile driving is on, you're getting up to 190, 195 dBs SEL. Pretty loud, would have caused TTS if there had been a humpback whale sitting there. And 10 times further away, you get that 15 or so dB decrease in sound level. But this site, 9,100 meters away, was in deeper water and closer to shipping. So the average daily SEL is actually quite a bit louder than it is closer to where the pile driving occurred. Next example, another seismic survey one where you see this big gap, but we were within sort of 40 kilometers of the seismic survey throughout the entire 2 months, and so the levels aren't changing very much. The last two are the two coral reefs, and what stands out again with them, especially in the Great Barrier Reef with no activity, is that the sound exposure is fairly loud, above 160, and it's flat. It just doesn't change. And it's dominated by snapping shrimp every evening. And so that snapping shrimp sound is right within the passband of all of the weighting functions. You just don't, they're all the same. They just all look the same. Over in Paradise Reef, though, by the 500 meters from the cruise pier, you are seeing the lower frequency weightings have more sound exposure because of the ships coming and going every day. But you'll also notice that every 2 weeks, there's a huge spike in the Dalhousie weightings. And that's because there's one particular vessel that came in every 2 weeks that did not turn off its echo sounder. And so what you're seeing here is a 27 kilohertz of the echo sounder coming through and showing up as these spikes. Loud enough that if for some reason a porpoise had hung out there, they would have gotten a permanent threshold shift. Now, there's not a lot of porpoises that hang out on coral reefs, so it's not likely to be an issue, but it's an interesting observation. When I was doing this work, I took things a little bit further and said, well, what else can we learn from the sound exposure level? And what I worked up is that if you autocorrelate your 1 minute sound exposures, so not the level, not the 10 log version, but just the raw linear level, every minute, and autocorrelate it, there's a pretty dramatic difference between areas with and without human activity. So what you're seeing here is the autocorrelation coefficient versus the lag in time in hours. And so in the Chukchi case or the Orphan Basin before seismic, let's just focus on the black, the low frequency weighted. It's staying up in both cases over pretty long time periods, which means if you know the sound now in those locations, you've got a pretty good chance of predicting the sound, say 10 hours from now or 5 hours from now, because it stays correlated. But if you have a location, say like Carson Canyon with the seismic and the fishing, or Vancouver, you can't predict the sound 15 minutes from now because the random effect of the shipping is so significant on the soundscape. The other one I wanted to point out is the reefs. When you have a natural reef, like the Great Barrier Reef, that autocorrelation is hitting like 90–95% a day later because the sound is so driven by this biologic activity that's linked to the solar activity. Paradise Reef, you definitely get a bump at 24 hours, but there's so much that relies on the shipping that it's not consistent. It's not jumping up. But you do see this 10-hour lag, which is how long that vessel was sitting in harbor when it showed up. So the autocorrelation on your Dalhousie weightings shows this big effect. Looking at this over time, so now taking 1 month for every month doing an autocorrelation. This is the the Orphan Basin data of Newfoundland, and so we go from August down to July, and in the periods when human activity is ongoing, which is essentially sort of June, July until October, November, we're seeing some pretty interesting patterns in our autocorrelations. September doesn't look bad, but August, October, and then June and July, the low frequency weighted autocorrelations are just dropping off pretty quickly. But throughout the winter, it's staying up because there's no human activity. Everybody's run for the hills because the weather's so bad. So that leads me to the supposition or the statement that we can define a natural soundscape using the sound exposure level. For open ocean, if your daily SEL is below 160 dBs, 3 micropascals per seconds, and the LFC weighted is within 3 dBs of that, plus the LFC SEL autocorrelation coefficient is above 0.6 after 3 hours, you can be pretty confident that there is very little impact of human activity on that soundscape. For coral reefs, because of the diurnal pattern that we get, or dial pattern, you can change that a little bit, and you have the 10 hertz and above SEL below 170, and for all the weightings, you should have an autocorrelation greater than, say, 0.75 after 24 hours. You've got a natural coral reef soundscape. From these data, we can take things and make recommendations of how to record data over long periods of time if you want to do an SEL analysis. I'd say use a minimum of a 1 minute recording. You want to record it at least 64 kilohertz. And if you're in an environment that you're not expecting a lot of human activity, you can probably get away with a duty cycle as low as 1 every 30 minutes. But as you're expecting more and more human activity, you're going to have to record more and more often. To the point where, say, you actually want to use this for a regulatory assessment, then you're going to have a continuous recording. But if, say in that Vancouver, where it's a lot of continuous sources, maybe 1 minute every 5 would be enough. And there are figures in the paper this comes from that shows the relationships there. The last thing that I propose you can do with SEL is define effective quiet. So effective quiet is the threshold below which animals' hearing starts to recover. So if they were exposed to loud sound and then that sound level drops below this level of effective quiet, their hearing can recover. And I propose that you can define that based on the 1 minute weighted SELs. And if they're, at least in the marine case, 31 dBs below Southall 2019 TPF threshold for non-impulsive sound, you're not going to accrue any hearing injury. And there's only probably 6 or 7 papers that have measured effective quiet, but all the thresholds they measured were above these levels. So these are very conservative, but they're really easy to find because you just take essentially 10 log of the number of minutes of a day, which is 31, from the thresholds, the daily thresholds, and you've got your effective quiet. Probably should use a different term for that, like no possible disturbance or accumulation cutoff or something like that, but it's a useful metric to take into consideration. The other thing that this allows you to do is that there's quite a bit of debate in the marine community about if you have an impulsive source, at what range from that source can you stop accumulating it as impulsive and it start accumulating it as continuous. And if you couple this effective quiet with an impulsiveness metrics like kurtosis, which some work I'm starting to go through, it shows that by the time the sound level drops below this threshold, it hasn't really lost its impulsive characteristic. So that transition from impulsive to continuous for accumulation doesn't matter. If it starts as impulsive, it's always impulsive. Don't worry about it. So finally, what other soundscape qualities should we want to quantify? One definitely is this impulsiveness, because it makes such a difference for hearing injury, and all we can do right now in the marine world at least is try and regulate to reduce injury. We need to know if there is an injury-related impulsiveness. So can we correct sound exposure for the relative amount of impulsiveness and have a single metric? There is some work that's been going on in China with factory workers and being replicated to a certain extent with chinchillas to show that at least in the terrestrial mammal case, it looks like you can do this. So perhaps there's a possibility to do that for other animal groups. Periodicity. As I mentioned, there's lots of evidence that if an animal can predict an impulse, it can protect itself when the next one comes in. So periodicity of signal is going to matter. As I mentioned earlier, fish and invertebrates use particle motion. They do not use the kind of hearing the mammals have. So at some point, we're going to have to really start delving into particle acceleration and displacement metrics. Those are all to do with injury. Then we can get into a more perception-based kind of approach potentially, especially as we get into trying to understand behavioral responses. So can we get into animals and perception? Can we define pleasantness and unpleasantness and link that some way to a metric we can measure? Or interesting or boring, or peaceful and stressful? And then finally, there's the issue of masking. That zone 3 I had in an initial figure. Masking potentially is the most insidious or pervasive of the effects of human sound. Because if an animal can't hear its conspecifics, its mate, its children, or it can't hear a predator coming, or it can't hear environmental cues, that can have some pretty long-term consequences on its fitness. So there's energy masking, but there are those who argue that energy masking is quite inconsequential. What you have to be able to actually evaluate is informational masking. In that case, we have to be able to say, well, how do animals look at co-modulation of different frequencies to protect themselves? Or do they do dip listening in between sounds? Or do they turn their heads and get spatial relief from masking? All things that some of these soundscape metrics should be able to get at in the future, but we're going to have to do a lot of work to get there. So thank you for listening to me drone on. A lot of this work I did when I was finishing my PhD with David Barclay at Dalhousie. And great thanks to JASCO for sponsoring us. The Environmental Studies Research Fund here in Canada that sponsors a lot of the work off of the East Coast. Shell Global Solutions for 2 or 3 data sets. Observe Ireland, University of New Hampshire, and the not funded ADM project where we're working with UNH, and the Block Island Wind Farm. And I'm done.
Okay, thank you, Bruce. The way we usually do this for the participants out on the web is we let you ask questions via chat, and then I will relay those to Bruce. That's the easiest way to do it. I see Dale Chase has actually already asked a question. He says, do non-human sounds have similar effects? But I don't understand the context. So I'll leave that one. So if you have a question, please type that in, and I will ask Bruce.
On the one about the non-human sounds, I think if they have the same characteristics, we'd expect them to have very similar effects. So if there's some kind of very loud, continuous sound, it would probably have some, at low frequencies, it in all likelihood would have had the same kind of masking effects as a ship would.
I have a question. This is Tony from UNH. I have a question while we're waiting for anyone else to send in a chat question. Your ACI definitions kind of scared me because they depend on so many things. Are they generally useful? You said that they're, what do you call them? They're detectors in some sense. They depend on bandwidth, time windows, frequency bands. Are they generally useful for comparisons with other studies, for comparisons over time? That much ways to change the metric just kind of is frightening.
Yeah. So when those became in vogue, for lack of a better word, there's a lot of results from the terrestrial world that were showing good results in identifying biodiversity, or at least chorusing, using the ACI. And a lot of stuff that was written just providing numbers, and they were all over the place. And I had exactly the same hesitations that you just expressed there, Tony, which is why I did that study, to try and understand what the thing is providing. And so when I presented it in New Orleans, there was several other seasoned researchers, for lack of a better word, that went, yeah, we tried that, it didn't work so good. But the results aren't published showing that. So there are results saying this is a wonderful thing, and it's used by Farina and his colleagues in something called EDDI, which in their case, which is often trying to identify bird populations in the Mediterranean, does work well. But in general, no, I don't think it's going to be that useful for all those factors.
But it sounds like what you said, it's been used as a detector, more or less.
People have been trying to use it as a detector that will find everything. That was its promise. That was the hype, and it can't do that.
Okay. All right, we have another question. This is from Dimitri Ponarakis, and he says, with the A weighting, it's based on a 40 Fon equal loudness contour. However, as the sound, 40 Fon, PHON. However, as the sound gets louder, the weighting curves flatten out, C and D weightings. Is this something that might be taken into account with M weightings in the future?
I've heard that question asked in several offline conversations, and we don't have enough information to go there. To my knowledge, the weightings that are in the Finneran work and the Southall work, those are the only animal-based weightings that are used at all besides human. So they are much more representative of the A weighting for sure. And then we turn around and use them for impulses. So yes, there's definitely some weaknesses there, but it's the best we've got. And I think there's an enormous amount of biological studies that have to be done in controlled conditions to try and get at that question and a lot of other ones. For instance, about impulsiveness and protection of hearing and sensitivities of other species groups. So yeah, if Dimitri has some ideas for how to evaluate that, I think the folks that do those kind of tests would be happy to try and find funding to do it.
Okay, thank you. Any more questions? Anyone at UNH have questions? We have about 11 here, I think. I think we're finished with questions. I'll ask one more before I remind everyone to send in their numbers that were at their watching groups. One last question I have is: are chinchillas are they so close to human hearing that that's the common thing to use? I'm not a biologist, so this is interesting to me that you mentioned chinchillas about 10 times.
Yeah, they appear to be. They appear to be the go-to animal that is relatively easy to raise and has a hearing system that is sufficiently close to humans that it's a good surrogate. I've seen some stuff from cats and dogs, but any of the really large sample size work has been done in chinchillas.
Okay, so I have 7 folks from URI. I think we ended up having 12 here. Anyone else want to send those in? I'll be watching. And if that's it, thank you, Bruce, and thank you everyone for listening in. And we'll see you. I need to remind you. Let me see if I can pull this up. I'm going to stop you. Oops.
I can stop sharing. Yep.
Yeah. So I'm going to pull up something. All right, so I think I'm sharing. Am I sharing now? Can you see that?
Yep.
Okay, so we have the next seminar will be on the 8th of October, same time at noon, and that's going to be given by Valerio Mazzoni. I think I have something here in the way. On agroacoustics and biotremology, whatever that is. I guess we'll find out on 8th October. So join us next time for that, and thank you for listening. Go on. Thank you, Bruce.
Thanks, Tony.